Okay, hey everybody, let's get started. So we'll start with chapter 2 today. Let's start with 2.1. Okay, so for these first bits of questions, if you're just looking at the homework problems, let's start with, first let's just talk about like a little bit of like a definition type thing. So say if we have a graph, how do these ones look? Let's make that a little bit better. Okay, so this first bit, so it's asking you to see, okay, where is a function increasing, decreasing, and constant? And basically what that means is, so we look from left to right, and increasing, this kind of intuitively means we go up. This is from looking from left to right, and decreasing means we're going to move down, and then constant means we move just horizontal. So if you notice, maybe call sort of like separate these little pieces into, or this graph into sections. All right, we could label this. Let's call this just A, B, and then C. So if we look on this graph, you see how if we're looking from left to right, so into this direction, the graph is moving upwards until the point A, and then from A to B, we're moving downwards again. From B to C, where it's kind of horizontal, and then from C on to infinity, the graph is moving upwards. So when we want to know, so where's this graph? Say increasing, decreasing, and then constant. So when the question asks, where is this, we're talking about x values. So, what are the x values that the graph is increasing? So another way of saying this is, so what are the x values? Where 1, 2, and 3 are happening. So we look at this graph above. So let's talk about 1, which is increasing. So again, we look at this picture. The graph is moving upwards from minus infinity all the way up to the point A. So either moving up or moving up or moving up or moving up, but then we stop right there at the point A. So we know from minus infinity to the point A, the graph is increasing. And we always use parentheses with these. Okay, so now the graph moves down a little bit, so it's not increasing there. The graph moves horizontal, so it's not increasing there, but then it starts moving up again from the point C on to infinity. So union C all the way to infinity. Whoops, put that back. Okay, so now let's do decreasing. So the graph's going to be decreasing. That means we move down as we look from left to right. Well, it's moving down here from A to B. So I know it's going to be decreasing from A to B. But then it moves horizontal here, and then it moves up again. So it doesn't decrease. It only decreases in that one spot from the x values from A to B. And then the last bit, which is constant. So the graph moves up here, so it's not constant. Then it moves down, so it's not constant. But it moves horizontal here, so it doesn't do anything. It is constant. So it's constant from B to C. And then it increases again, so it's not constant. So these are the intervals where it happens. So we're decreasing, so on the x values of minus infinity to A all the way up to C to infinity. The graph is decreasing from the x values of A to B, and it's constant from the x values B all the way up to C. And so that's basically it for these problems. You could give, like, if you look, these are like similar to problems, I guess 1 through 6. What else do we have to do? What's 15 say? 15 similar. Basically, just look at the graph and say if the graph is moving upwards, then it's increasing. If it moves downwards, and we look from left to right. So if we look from left to right and the graph moves up, it's increasing. Looking from left to right, if the graph goes down, it's decreasing. And then if it just moves horizontal, it's constant. So the next thing, if you look, let's see, the next bit of homework is telling us to find relative maxins and mins. So let's just talk about that. So say this graph, sort of this problem explains what these things, so increasing, decreasing, and constant. Another thing that we need to be able to recognize from graphs, let's just draw another picture, say something looks like. I'll draw this a little bit better. So the next thing we need to recognize are relative max and mins. And with a relative max and a min, so a max, this just sort of means like the a top of a hill. And then we can think of a relative min as the bottom of a valley. So like a top of a hill, let's do these with green. So the relative maxes in here are going to be this point, that's the top of the hill. This point right here, that's the top of a hill. And that's all we have. And so now let's do the relative mins. Let's do that in red. So if you look at the relative mins, all it is the bottom of a valley. So we have a little bottom piece right here. And then we have a piece right here. So as far as relative max and min go, that's basically it. Just kind of like, definitions to have memorized. And I guess we could like label these. Say if this was the point minus 7, 5. Let's just call it that. We can call this one maybe minus 3, minus 3. Let's call this the point 1, 6. And we can call this the point 5, 1. So say if we just label these points, just making them up. What we could say is then, and this could be the graph of f of x. So above we could say f of x has 2 relative maximums at the points x equals, so the first one's at x equals minus 7, and the second one is at x equals 1. So at x equals minus 7, we're just saying that's a 1 relative max, and then when x is over here at 1, so here's minus 7, here's 1, we have another max. So, and then we can say f of x has 2 relative minimums. See, at the points. Then we can label this. We said this one was minus 3, and over here this was 5. So the first one was at x equals minus 3. And the second one was at x equals 5. All right, so as far as relative max and min go, that's basically all we need to know. Is that just if the top of a little hill is a max and the bottom of a hill is, or the bottom of a valley is going to be a minimum. This right here, this point, this isn't anything particular. This just means the graph keeps going up and up and up. So the relative max and mins, they have to have like this little shape. It goes up and then it goes down, or it goes down, then it starts going back up again. Just moving upwards doesn't give us a maximum. It has to be like a top of a hill or a bottom of a valley like this. Okay, what's the next question we have to do from this section? Okay, we'll do several of these. This is gonna be like examples like 35 through, or numbers 35 through 48. So graphing. Graphing piecewise functions. So we were graphing, we've graphed lines before in one of the earlier sections. We could do it several ways. Let's just do like a basic example first. Say if we want to graph f of x is equal to, I don't know, 2x minus 3. So there's several ways we could do this. We can make like an x and y table, or we can just start with the y-intercept and use the slope and do like the rise over run method, or we could just find two, because we know for a line all we need is 2 points to graph it. We put 2 points on and connect those 2 points with a line, and then that'll give us the graph of it. And the way we can come up with points is like an XY table. So let's do that method, because that's how we're going to be graphing these piecewise functions. So we're going to graph this, graph this using an XY table. All right, so we can start with an XY table, and there's no particular x values we need to plug in. Any is okay. So we could start, say, plugging in -1. If we plug in -1, remember here y is equal to 2x minus 3. So if y is -1, we're going to get 2 times -1 minus 3, which is -5. So that's 1 point on the line, -1 minus 5. Maybe we can plug in the point 3. So we would get 2 times 3 minus 3, which is going to be equal +3. So we have these 2 points. So when x is -1, we get -5, and when x is 3, we get 3. So let's go on to a graph. Here's -1, 3. At -1, it's -5. And at 3, it's 3. So here's the point 3, 3. And then here's the point -1, -5. Let's move that actually. Oops. Oh, it was -1, -5. All right, so for a line, we just need 2 points, and then we're going to connect it. So notice sometimes we need more than 2 points. Like if we have a quadratic, we need more than 2 points to graph it. But this is only with a line. So with a, let's write that down. So with a line, and when we mean line, what we mean is y equals mx plus b. We only need 2 points to graph. Okay, let's put that in parentheses. All right, so here we made an XY table. We've got 2 points. We connected them with a line, and this would be our answer. This is the graph of that line by using an XY table. So with this idea in mind, let's talk about what a piecewise function is. So this right here, this function f of x is 2x minus 3. Any x value we want to plug in, we can just plug into this line right now. We can plug in 50 for x. We could plug in minus this x value right here. And we could plug in -20, -1,000, -1,000,000, 4,000,000, any number we want. But with the piecewise function, it's going to be a little bit differently. Let's just do that piecewise function. So a piecewise function is written like this. Just make one up real quick. There's a brace or a bracket, and we'll have several equations on the inside. So maybe we have 2x minus 1, and then there's going to be a condition. So this might be x is bigger than or equal to 2. Actually, let's start with less than or equal to 2. And then maybe 3x plus 3, x is going to be bigger than 2. So what this is telling us is that when we want to plug in an x value less than or equal to 2, we have to use this top equation. When we want to plug in an x value bigger than 2, we're going to use this bottom equation. So let's just give a couple examples here. So say if we want to find the value of f of, say, f of minus 3. Well, this is the x value we're plugging in here. So this is the x value. And so we have to look. So is minus 3, is that included in this section or is that included in this section? Well, minus 3 is less than 2. So it's going to be included in the top section. So what we're going to use is the top equation for this one. So f of minus 3, this is going to equal 2 minus 3 minus 1, which is minus 7. So let's do f of 0. So again, here's the x value. So we see is 0, what section is it going to be, in this section or this section? Well, 0 is less than 2, so we have to use the top equation. So this is going to be 2 times 0 minus 1, which is minus 1. We could plug in 2. So we see what section is 2 in. So is 2 less than or equal to 2, or is 2 bigger than 2? Well, 2 is less than or equal to 2 because it is equal to 2. So again, 2 is going to be in this section. So again, here's our x value. And then we're going to use our top equation because 2 belongs to this section right here. So we'll have 2 times 2 minus 1, which is 3. We could plug in now just like another number, maybe like f of 5. So again, now here's our x value. So what section is 5? So 5 bigger, less than or equal to 2, or is 5 bigger than 2? 5 is bigger than 2, so we're going to use this bottom equation. So we're going to have 3 times 5 plus 3, which is 18. And so that's just sort of the idea of a piecewise function. We're given, 15 plus 18. We're given a couple equations and a condition about the x value. So wherever the x value we're plugging in, we have to look over here first and see what section is it in. And whatever section it is in, that's the equation we're going to use. Let's do another example. So maybe something like f of x equals 7 if x is less than or equal to minus 1. 0 if minus 1 is less than x, which is less than 1. And then say 2x if x is bigger than or equal to 1. So here we have 3 sections. So let's say first we want to plug in the value f of minus 3. Okay, so where does minus 3 fall? That's going to be this top one. See, minus 3 is less than or equal to minus 1. So we're going to use our top equation. But what this top equation is saying, 7, is just no matter what x value we plug in, we're going to get the number 7. So f of minus 3, that's just equal to 7. Say if we're going to do f of minus 2. So same thing, minus 2 falls in this top section. So minus 2 is less than or equal to minus 1, so we're going to use the top equation, which again is just 7. How about f of negative 1/2? Well, negative 1/2 is not in the top section anymore. Negative 1/2 is not less than minus 1. But minus 1/2 is in this middle section. Minus 1/2 is in between minus 1 and 1. So for this one, if you look at the equation, it says 0. So any x value we plug into this section, we're going to get 0. So f of minus 1/2 is 0. Again, 0 is in that middle section, so f of 0 is going to be 0. F of 1/3, so 1/3 is in this section. So that's going to be 0, and so on. So now let's talk about the bigger section. What about when f of 1? Well, 1's not in here because 1's not less than or equal to 1. 1's not here because this is value strictly less than 1, and 1's not strictly less than 1. If we go down to the bottom section, we'll see that 1 is in this section because 1 is bigger than or equal to 1. So then we plug 1 into the bottom equation, which is plugging 1 into 2x. So this is going to be 2 times 1, which is equal to 2. Say if we're going to do f of 7. So again, 7 is bigger than or equal to 1, so it's in this bottom section. I'm going to do 2 times 7, which is equal to 14. So yeah, so here this is like a quick little example of a piecewise function that's got more than 2 equations. It has 3 equations. It doesn't matter how many you have, so it's just always the same rule. Whatever the x value is, you look over here, you find where the x value belongs, and that's the equation you're going to use. Right, so let's do a couple of examples of graphing these. Start with, we can start with, is that a homework problem? No, that's fine. 35. So we want to graph, is that what this is saying? Yeah, just graph. G of x is equal to x plus 4 if x is less than or equal to 1, and 8 minus x if x is bigger than 1. So do a sequence of steps to graph these. So we want to use an XY table. And we're going to start, we look at the number, whatever number is written on the right-hand side, so this column over here. In this example, all we see is the number 1. And so what we want to do is we're going to make 2 XY tables, one for this top equation and one for this bottom equation. Let's just actually start with doing that. So let's say we want to label these a little bit. Let's move this bracket over. This can be like equation 1, and this is going to be equation 2. Okay, so let's talk about, here's like the XY table for equation 1. So we have x, we have y. In this situation, y is equal to x plus 4. And then for equation 2, here's our xy table. In this situation, our y is equal to 8 minus x. But now we kind of want to be a little bit careful about the numbers that we plug in here. So for example, like we could, so you see how the equation 2, this is only for x values for x bigger than 1. So it's not like we're going to want to plug in minus 3 to this one, because that's not going to do us any good. When we plug minus 3 into g, we don't use this equation. So we need to be a little bit more careful now when we're plugging in x, y values. Regardless, the first thing we do though, is we always plug in the number that we see over here. In this situation, we only see one number, it's 1. You see here is x is less than or equal to 1, here's x is bigger than 1. So for this, we're going to plug in both of those numbers, that number to both of these equations. So let's just do that right now. X is 1, x is 1. Maybe what you're thinking though right now is that for this bottom equation though, you see how this says x is strictly bigger than 1. So technically we're not allowed to plug 1 into that equation. If we were going to plug in 1, we would use this top equation because 1 belongs to this section. However, when we're graphing the piecewise functions, whatever numbers we see on this side, meaning like here we only see the number 1, we plug this number into both of the equations. Really what we actually do is we look to the right. So we look at this box right here, and whatever numbers we see over here, no matter what, if it's less than or equal to, we plug it into the equation. So here we have a 1, so we're going to plug 1 into this one. If we look over here, there's a 1, so we're going to plug 1 into this one. This will be more apparent. We'll do a couple more examples, and you'll see what I mean by this. So when we plug 1 into this, look at equation number 1 over here at the xy table. When we plug in 1, so you plug in 1 to the right-hand side, we'll have 1 plus 4, which is equal to 5. All right. And then on this right equation number 2, when we plug in 1, we'll have 8 minus 1, which is equal to 7. And now what we're going to do to kind of like remind us that we're only allowed to plug 1 into this one. We're really not allowed to plug 1 into here. Let's put a closed dot next to this 5. And we're going to put an open dot next to this 7. So the reason why we're doing that, closed dot always means, like when we're thinking about like a number line, whenever we wrote like, say, whenever we write a closed dot, that means we include this number, the number that we're putting a dot on. Whenever we put an open dot, it means we're excluding that number. It's like we're getting a hole punch and punching it out. So that's what we're this closed dot kind of reminds us that 5 is actually included. So if we plug 5 into G, we plug it into this top equation. We don't plug it into this bottom equation. So that's why this open hole is here. All right, so now what we need to do for each section, we need to pick one more point. So we need to pick another point to plug into equation number 1. So if we look at equation number 1, that's for x values less than or equal to 1. So we could plug in, say, 0. If we plug in 0 here, we'll get 0 plus 4. That's equal to 4. On equation number 2, that's for x values bigger than 1. Say we could plug in 3. So 8 minus 3, that's equal to 5. And we're allowed to plug 0 over into equation number 1 because 0 is less than or equal to 1. So we're going to put a closed dot next to this one. For 3, if you look at 3 is bigger than 1, so we're allowed to plug 3 into this bottom equation. So we're going to put a closed dot over here. Okay, so the next thing we're going to do now is we want to draw our graph and put the dots, plot those points on the graph. So at an x value of 1, we're going to have a closed dot at the point 1, 5. So here's 5, have a closed dot there. And then also at 0, we're going to have the point 4. So here's 4. At 0, it's going to be 4. And then what we're going to do is we're going to connect those two. But we start at this point and we move towards 0. So we're going to draw it like this. Okay, so that takes care of equation number 1. Now equation number 2, we're going to have an open circle at the point 1, 7. So here's 7. We have an open circle. And then we're going to have a closed circle at the point 3, 5. What did we say this was? This is 1. Yeah, at 3. And then say at 5, we had a closed circle. And then we're going to connect this point to this point. Okay, and that's all we need to do. So then we're done graphing this piecewise function. So let's do another example like that. Let's do 42. Okay, let's move the bracket over so we can label these equations again. Here's equation 1, here's equation 2. So let's do the same thing. The first step was we can see this. So if you look, that's kind of hard to, I don't have enough room to put it on both on the same screen. We start with the XY table. So here's an XY table for equation 1. Here's an XY table for equation 2. And here y is equal to 2x minus 1. And this is y is equal to 2 minus x. Okay, so like we said, we look to the right of the equation, and whatever numbers we see, we plug into that equation. So if we look to the right, the only number we see is 2. So we're going to plug 2 here. Same with this one. You look to the right, all you see is the number 2. So we're going to plug 2 into this one as well. So that's always the first step. So what happens when we plug 2 into the left? We get 2 times 2 minus 1, which is equal to 3. And to remind us that, so you see here, we're technically not allowed to plug 2 into this equation because it's a less than sign. 2 is not less than 2. 2 is equal to 2. So for that reason, we're going to put an open circle. And then the 2 on the bottom, we plug that, we're going to get 2 minus 2, which is equal to 0. And we're allowed to plug 2 into here because you see 2 is greater than or equal to 2. So we're going to put a closed circle next to that 0. Let's move this open circle so it doesn't look like a 30. Okay, so now let's plug in 2 more points. So to this top equation, we're allowed to plug in points that are less than 2. So let's plug in 0. If we plug in 0, we're going to get 2 times 0 minus 1, which is equal to minus 1. And we're allowed to plug in minus 1 to that. Or, I'm sorry, we're allowed to plug in 0 to this section because 0 is less than 2. So we're going to put a closed dot here. What's another number we could plug into this section? It's like 7. If we plug in 7 here, we're going to get 2 minus 7, which is equal to minus 5. And again, 7 is bigger than 2, so we're allowed to plug 7 in here. So this is going to get a closed dot as well. All right, so now just like before, we're going to put all these dots onto a graph and connect them. Okay, so at 2, if we look at equation number 1, we have an open circle at 2, 3. And then we have a closed circle at 2, 0. Because see over here, when x is 2, we get 0. So we have a closed circle at 2, 0. If we look over here at the point 0, we're going to be a closed circle at minus 1. Closed circle, minus 1. And so the one we connect is, well, we're connecting from this point, this top point, down to this point. So we're connecting from, sorry. So we connect from the point 2, 3 down to this point 0, minus 1. So from 2, 3 down to 0, minus 1. Okay, and then so you see over here we have the point 2, 0 with a closed circle, then the point 7, minus 5 with a closed circle. And then we connect those. And so then here will be the graph of this function. Let's do one that has 3 equations. Kind of like, let's see. 1, 3. Or we could do 38. So the first equation is minus 5x minus 8. And that's for x values less than minus 2. The second equation is 1/2 x plus 5. That is for minus 2 up to 4. And the third equation, 10 minus 2x. And that is for x values bigger than 4. Okay, so now let's make our xy tables. Now we're going to have 3 because we have 3 equations. So here's for the first equation. The first equation being minus 5x minus 8. We have a table for our second equation. This one is 1/2 x plus 5. And then we have a table for our third equation. That was for y is equal to 10 minus 2x. So we start, now let's plug in some points to these. So remember how we said we go to our equation, we look to the right, and whatever numbers we see, we plug in. Here's equation number 1. We look to the right, all we see is the number minus 2. So we're going to start by plugging minus 2 into equation number 1. With equation number 2, if we look to the right, we see 2 numbers. We see the numbers minus 2 and 4. So let's plug in minus 2 and then 4. To the right of equation number 3, all we see is the number 4. So we're going to plug the number 4 in here. And remember how, so for lines, we need 2 points for each table. The middle one already has 2 points, so we don't need to add any more points to there. We're going to need to add 1 more point for this equation. Let's move this 3 above. And then we're going to have to also have 1 more point to this equation over here. So let's just start. So what happens when we plug minus 2 into this equation? So we get minus 2 times minus 5. Minus 5 minus 2. Then we subtract 8. So that's minus 2 times minus 5 is 10. 10 minus 2 is, or 10 minus 8 is 2. So we get 2. Sorry, I'm going to squeeze this over a little bit more. And so 2, or we plugged in minus 2 here. Minus 2 is not in this section. Minus 2 is not less than minus 2. It's equal to minus 2. So we're going to put an open dot. So we have an open dot there. I want to make sure it doesn't look like a 20. I don't know, maybe we'll put like a comma or something. Maybe that makes it look harder to read. We'll put like a semicolon and then put an open dot. All right, so now let's plug another number into this section. So another number into the section, we have to choose 1 in this interval now. So something less than minus 2, we could choose like minus 5. So if we plug in minus 5, we're going to get minus 5 times minus 5 minus 8, which is 25 minus 8, which is 17. And then we're allowed to plug minus 5 into here, so we're going to put a closed dot. Okay, so we only need 2 points in each section, so that section's done. So now this middle section, what happens when we plug in minus 2? So we're going to get 1/2 minus 2 plus 5. So 1/2 times minus 2 is minus 1. Add 5, we get 4. And minus 2 is in this section, see? Greater than or equal to sign. So minus 2 is greater than or equal to minus 2. So this one is going to get a closed dot. And then 4, 1/2, 4 plus 5. So 1/2 times 4 is 2, 2 plus 5 is 7. And again, we look over here, less than or equal to 4. So 4 is in that section, so we get a closed dot there. All right, so that middle section's done. Equation number 3. So we plug in 4. So that's 10 minus 2x. So we get 10 minus 2 times 4, which is 2. And 4 is not bigger than 4, so we have to put an open circle here. And then plug another thing in that section, so something bigger than 4, like 6. We would get 10 minus 2 times 6, which is 10 minus 12, which is minus 2. And this one gets a closed circle because 6 is in that section. So now each of our tables have 2 points, so we can draw this graph. So let's start with the equation on the far left. At the point minus 2, 2, we have an open circle. And at the point minus 5, 17, we have a closed circle. And we connect those 2 dots together. You only connect dots together that happen on the same table. So you see on this table over here, just the minus 2 and the minus 5, we connect those dots together. Now we move to the middle table. At this one, it says at minus 2, we're going to be 4. At minus 2, it's going to be 4. And with a closed dot. And at 4, it's going to be 7. And then we connect those 2 dots together. However, we stop in the middle like that. There's no more arrows because this middle equation, equation number 2, is only for in between minus 2 and 4. So we just draw a line in between the x values of minus 2 and 4. Okay, now for the last equation, it says at 4, 2, we're going to have an open circle. So at 4, 2, we have an open circle. And then at 6 minus 2, we have a closed circle. And then we connect those dots together. Okay, and then so this would be the graph of the piecewise function. Okay. So that kind of takes care of this section. Let's move on to section 2.2. Okay, so we got going on in here. 1.3.13. Let's write down a couple definitions. So there's a notation that this book uses that, say definition. So say if we just have, so f of x and g of x are functions. We have a couple of things. The first thing we define is something called this, f plus g of x. And what this really just means is we add the 2 functions together. Another thing that we can define is f minus g of x. And this just means we subtract the 2 functions. And then we can have f times g of x. So this means we multiply the functions. And then the last one, f divided by g of x. And this just means we divide the functions. So the definitions are kind of intuitive. You know, f plus g, that would just make sense for it to mean add the functions together. Same with subtraction, multiplication, and division. So let's do an example. Let's say f of x is equal to 3x minus 1, and g of x is equal to about 7 minus 2x. And so let's find a couple of things. Let's find f plus g of 0. So using the definition above, this just means f of 0 plus g of 0. So what is f of 0? That's going to be 3 times 0 minus 1. And then what's g of 0? G of 0, that's just going to be 7 minus 2 times 0. So this is going to be minus 1 plus 7, which is equal to 6. All right, so how about g minus f of 3? So this is just going to equal g of 3 minus f of 3, which is going to equal, so g of 3, that's going to be 7 minus 2 times 3. F of 3, that is going to be 3 times 3 minus 1. So the first thing we have 7 minus 6, which is 1, minus, and then here we have 9 minus 1, which is 8. So 1 minus 8, which is going to equal minus 7. So we can do, how about f times f of about t plus 1. So just using the definition, this is going to be f of t plus 1 multiplied by f of t plus 1. And so this is going to equal, so what is f of t plus 1? So that's going to be 3t plus 1 minus 1. So just plugging in t plus 1 for f, which is right here. And then here's g. And again, f of t plus 1. So 3t plus 1 minus 1. So this is going to equal, we'll have 3t plus 3 minus 1 when we distribute the 3 on the inside of the parentheses. And same thing over here, 3t plus 3 minus 1. And so this is going to be 3t plus 2, 3t plus 2, which is just equal to 3t plus 2. We have 2 of them, so we'll just write 3t plus 2 squared. Let's do one more. How about f divided by g of 7 over 2? Okay, so this is going to equal f of 7 over 2 divided by g of 7 over 2. So this is going to equal, so what is f? 3x minus 1. So we'll have 3, 7 over 2 minus 1 divided by g. So 7 minus 2x. So 7 minus 2 times 7 over 2. So this is going to be 21 over 2 minus 1 divided by, and see how these 2's cancel? So we have 7 minus 7 on the bottom. And we don't even need to simplify the top, because you see the top, just leave it the same. 2 and 2 minus 1 over 1. And then the bottom is 7 minus 7, which is 0. So this does not exist. Okay. So there's a couple of examples with doing that. So that's kind of like similar to problems like 1 through 10. Okay. What else do we got? And I guess also the same thing as like 11 to 16. Go to 61. Where's 61? Okay, 59 and 61. Where's 29? All right, and 49. No. 29. All right, so let's talk about doing these with domain. Just to label these are called, does the book have a name for them? I think they're called combination functions. Just for labeling purposes, that's what we'll call them. So let's talk about the domain of combination functions. Okay, so domain of combination functions. So what we do is we just basically, let's do this is learned by an example. Say if we have something like f of x is equal to 1 plus 1 over x, and then g of x is equal to, how about 3x squared minus x. And now let's find the domain of, let's see, of the following. Let's start with just f plus g of x. So first thing to do, let's just write down what's the definition of this. Well, this just means f of x plus g of x. Okay, so what is f of x? F of x is 1 plus 1 over x. And then what's g of x? G of x is 3x squared minus x. And what we do now is we just take the derivative, or sorry, not the derivative, the domain of this without doing any more simplifying. So, okay, now let's find the domain. So remember, always think about two things with domain: fractions and square roots. So we look at this. Are there any fractions? That answer, oh, sorry, what's going on here? Okay, so are there any fractions or are there any square roots? There's no square roots here, but we do have fractions. There's one fraction. That fraction happens right here at 1 over x. So you remember that the bottom of a fraction can't be 0. So what's the bottom of this fraction? Well, the bottom of that fraction is just x. So because of that, we have to have x can't be equal to 0. But there's no other fractions in this problem, and there's no other square roots. So the only issue that we have when doing the domain in this is if x is equal to 0. So x can't be 0. So, we go to our number line. Here's 0. Put a hole punch on it. You get rid of it. But that's the only issue. Everything over here is okay, and everything over here is okay. So our domain for this one is this going to be minus infinity up to 0, and then 0 to infinity. Let's do g divided by f of x. Okay, so what is this equal to? Well, from the definition, that says g of x divided by f of x. And what is g of x? Well, g of x is 3x squared minus x. And then f of x is 1 plus 1 over x. And so now we don't do any more simplifying. Once we plug in the g and the f, we find the domain. So again, fractions and square roots. So no square roots, so we don't got to worry about that, but there are fractions. We see fractions technically in two different places. This entire thing's a fraction, and here's the bottom of that fraction. So we have to have 1 plus 1 over x. This can't equal 0. Okay? But we also see a fraction in one other place. If we look at the bottom of this fraction, here's a fraction, and the bottom of this fraction can't be 0. So x also can't be equal to 0. So these two things that can't be equal to 0, those are the bottoms of the fractions. We have this big fraction right here, and there's the bottom of this, so that can't equal 0. And at the same time, the bottom, we have a fraction right here. And so the bottom of that fraction can't be 0. So we have these two things we need to think about when we're doing the domain here. So if we look at the left-hand side, if we want to solve for x here, we can subtract 1 over x to the other side. So we'll have 1 can't be equal to minus 1 over x. Now what we do is multiply x over to the left. So x cannot be equal to minus 1. So that's what we get from this one. And this one we're done. We just see x can't be equal to 0. So on the number line, the two things that we have are minus 1, we're not allowed to be this, and 0, we're not allowed to be this. So because since there were no square roots, there was only fractions, these are the only times we have issues. The only times we have issues is when the bottom of a fraction is 0. So that happens if x is equal to minus 1 and if x is equal to 0. So we can't be those two numbers, so we get rid of them. But those are the only two issues. So everything else is okay. And then so for this one, our domain is minus infinity up to minus 1, minus 1 to 0, 0 to infinity. Okay. How about we do f divided by g of x. So just from the definition, this is going to be f of x divided by g of x. And so what does that mean? Well, f of x, that was 1 plus 1 over x. So we have 1 plus 1 over x. G of x, that was 3x squared minus x. Okay. So now let's find the domain. And just like always, so fractions, square roots. So there's no square roots, don't got to worry about that, but there are fractions. Again, there's fractions in 2 places. This whole thing is a fraction, and here's the bottom of the fraction. So 3x squared minus x, this is not allowed to be 0. And if we look at the top, there's a fraction in the top. That fraction is just 1 over x. So the bottom of this fraction can't be 0. So x is not allowed to be 0. So now let's solve for x in both of these. So here what we can do is we can factor out an x. We have x 3x minus 1. This can't be 0. So we set both of those pieces equal to 0. We get x can't be 0. And here we get 3x minus 1 can't be 0. So we're done at 3x. So x can't be 0. So we have to keep solving this 3x minus 1 thing. So we add the 1 over. 3x can't equal 1. Divide by the 3. X can't equal 1/3. So we have these cases. X can't be 0. X can't be 1/3. And again, x can't be 0. So now for this domain, what we do is we go to our number line. We have 0, and then we have 1/3. So we're not allowed to be 0. We're not allowed to be 1/3, so we get rid of those, but all the other numbers are okay. And so for this domain, we'll have minus infinity to 0, 0 to 1/3, 1/3 to infinity. Okay. Let's do one more problem. Or one more problem just like this. So let's do, how about f of x is the square root of x minus 3. G of x is going to be equal to 2 minus 3 over x. So let's find the domain. Of, how about g divided by f of x. So first thing we do is let's write that out. So g over f of x, this is equal to g of x divided by f of x. So what does this mean? G of x, that's going to be 2 minus 3 over x. F of x, that is square root of x minus 3. Okay, now we don't do anything else. Now what we do is the domain. So we see, or we want to ask ourselves, are there fractions? Are there square roots? The answer is yes to both of these. Let's deal with the fractions first. So first you see we have a big fraction right here. Here's the bottom of the fraction. So square root of x minus 3, this can't equal 0. The top has a fraction. The top has this fraction right here, 3 over x. The bottom of that fraction can't be 0. So x can't be 0. And then also we do have, so this part right here, this is just for fractions. We also have square roots. So the inside of our square root is x minus 3, so we need that to be bigger than or equal to 0. So this is the domain for both of our things. So for square roots, we have one square root, that's the square root of x minus 3, so we need the inside of our square root, which is x minus 3, to be bigger than or equal to 0. And we can't have the bottom of fractions being 0. So we have this whole thing being a fraction, the bottom of that fraction being this, square root of x minus 3, so that can't equal 0. And the top has a fraction. The bottom of that fraction is just x, so x can't equal 0. So now let's solve each of these things. So right here, square root of x minus 3 can't equal 0. If we square both sides, we just get x minus 3 can't equal 0. Add the 3 over, we get x can't equal 3. Okay, so this is important. Here, nothing to do. That's important. Here, let's add the 3 over. X has to be bigger than or equal to 3. So this is important. So we need to take all three of these things into consideration. So let's go to our number line. We start with the fraction thing first. So it says x is not allowed to be equal to 0 or not allowed to be equal to 3. So here's 0. Get rid of that number. Here's 3. Let's get rid of that number. Then if we go to the square roots, it's saying x has to be bigger than or equal to 3. But we already got rid of 3. So this is just basically means we have to be bigger than 3. So this is what we're shading is all we're allowed to be. So nothing else is okay. Everything else will give us a problem. So again, we're not allowed to be 3 and we're not allowed to be 0. So we get rid of those. And we also have to be bigger than or equal to 3. So this is over here is bigger than 3. And normally, since it's bigger than or equal to 3, we would have this shaded in with the closed dot. But because over here it says we're not allowed to be equal to 3, we have to take that into consideration too, so we don't have a closed dot. So then here is our domain. Another way of writing that is just going to be 3 to infinity. Okay, I think there's one more question we need to do. Difference quotient. So the difference quotient is this. So this is the difference quotient. So we're given a function f of x, and we just have to fill in these spots. So let's do an example. How about we got something like, there's 59. F of x is equal to x squared plus 1. Find the difference quotient. Okay, so what does this mean? Well, we need to find three things. We need to find f of x plus h, we need to find f of x, and then just put an h on the bottom. So really the only thing we need to find is f of x plus h. So we're already given that f of x is equal to x squared plus 1. So this tells us that f of x plus h, so again, we're plugging in x plus h now for x. So this is going to equal x plus h squared plus 1. See, whatever's on the inside, here's an x. All you do is you plug an x right here. So now on the inside, there's an x plus h. So we need to plug an x plus h in right here. We have to plug this x plus h in right there. That's why we have an x plus h squared. So now let's do a little bit of simplifying. X plus h squared, that's going to be, if we were going to FOIL that out, we would get x squared plus 2xh plus h squared plus 1. Or maybe we could just do it off to the side. So if we were going to do x plus h, you know, we do our FOILing. X goes to x goes to h goes to x goes to h. So we get x squared plus xh plus hx plus h squared. And then if we combine like terms, we get x squared plus 2xh plus h squared. And so that's why we have this piece right here. Okay, so then now let's see, is there any like terms that combined? Nope. So now we know that our f of x plus, so we have f of x is this, f of x is x squared plus 1. We just calculated f of x plus h. We got f of x plus h is equal to x squared 2xh h squared plus 1. So now all we have to do is just plug everything into the difference quotient. So we start by plugging in f of x plus h. So x squared plus 2xh h squared plus 1. Now minus f of x squared plus 1, and then all divided by h. Okay, so now let's just start simplifying. So this equals 2xh plus h squared minus 1. Now we have minus x squared minus 1. all divided by h. So on the top, the x squareds cancel, and the oh, this is a plus 1, sorry. Because you see here, f of x plus h has plus 1 at the very end. This needs to be a plus 1, plus 1. So you see the minus x squared cancels with the x squared, and then the plus 1 cancels with the minus 1. So what we're left with on the top is going to be 2xh plus h squared, all divided by h. And the last thing we can do is factor out an h on the top. So an h can be taken out of this piece, and an h can be taken out of that piece. And the last thing we do is cross out the h on the top and the bottom. So what we're left with is this. And so this would be what our difference quotient is equal to. Okay, takes care of that question. I think it's a good place to stop for the day. So yeah, this takes care of all the homework problems from 2.1 and 2.2. Yeah, so if anyone has any questions, feel free to email me about this. Yeah, otherwise I'll see whoever comes tomorrow. Cool, thank you.